In a previous video, Professor Jean-Yves Le Boudec discussed the need of smart grids to manage, among other things, the huge variability of renewable energy productions. This real-time big data management poses major technical challenges.
So the challenges are, in fact, similar to what we would call a cyber-physical system. So we have a physical system, which is the grid, with all the resources we discussed that you can play with. And now the problem is to do it really with an enormous amount of resources. So you don't want to have a huge optimization central controller that would be aware of everything happening everywhere in all the grids of a given country. So the problem is how to manage in a scalable way all these resources.
What makes this even trickier is that there is an underlying energy market.
The markets, energy is usually also linked to markets where if I do one of the things I said, for example, shift my consumption of electricity for my deep freezers, this shifting might be an energy product that I can sell on the market to a grid operator to tell them, if you have a problem now of overproduction, I can absorb your overproduction now. Or in contrast, if you have a problem of deficit of production, I can reduce my consumption because I have the ability to shift it over time. This reduction has the same effect as a generation of power. So it can be also sold on a market.
This all makes energy management extremely complex.
Combining all those pieces together makes it a huge cyber-physical system where there's a lot of information being processed at various timescales, the timescale of planning, but also markets, and also real-time operation.
Now, the management of energy flows can be regarded as an optimization problem. However,
this is a nasty optimization problem, where it is a non-convex problem because of the physical properties of electrical grids. So it is an optimization problem which is nasty in some sense.
By that, as often in computer science, we mean that there is likely no algorithm that can solve this optimization problem in a reasonable amount of time.
A lot of work is on how to relax it, make fine approximations that are good enough or that have guaranteed performance to this problem. That's one area of active research.
But there's even worse.
Another area is how to make all this happen in real time or quasi-real time. For example, if we're managing a charging station, that's one of the examples on which we're working, on charging station for electric cars. We're talking here of 100 or 500 superchargers for 500 cars that consume 30 to 50 kilowatt each. So we're talking of large numbers that are equipped, for example, with solar panels to reduce the power consumption and the stress on the grid. We need to manage the flows such that when there are clouds, for example, that are coming, we react very quickly to change the set points so that the grid does not suffer. For example, if we were allowing all the cars to charge at very high power because we have a lot of sun that is coming now, and then a cloud comes and within a fraction of a minute all the local power generation is reduced by 60%. If we do nothing and if we draw this excess power from the main grid, that might cause congestion on the lines, for example. So we have to react within seconds, or in some cases fractions of a second. So we have to do real-time systems.
And just like when you're driving a car, real-time management requires anticipation, which is a huge problem in itself.
One example is if you're managing a grid and you want to avoid congestion on some of the lines, and you're controlling some resources. For example, you have the new things like your electric charging station, which is a big asset in which you will invest in a controller and a battery. But this happens to be connected to a grid somewhere on which there are buildings like this one with traditional equipment that you don't want to control individually, all of them, because there are too many of them and the cost of controlling each and every apartment and what everyone is doing would be large compared to the impact of each of those. So what can be done in a case like this is, using machine learning techniques, do a short-term prediction of what would happen to all those parts of the system that we don't control.
Of course, making predictions about the future is difficult, but not all predictions are impossible.
It turns out it's possible. It's impossible to predict exactly what you and I will do in 10 days from now, for example. It's possible to predict in aggregates. It's possible to predict fairly accurately what a large country will do in terms of power consumption. But an individual small load is hard to predict. But it's easy to predict at a very short time scale. So if this controller has to take a decision about the power flow that goes in or out of the battery or into the electric cars that are charging, and see whether this is compatible with the flows that are generated by the other loads, so the heaters, the people watching their TV, etc. For this, you need to be able to do a forecast of what those other uncontrolled resources will be. And this is a place where machine learning techniques work well.
But perhaps the greatest of all challenges for smart grids is to guarantee their reliability. And given their immense complexity, you can guess that this is a huge difficulty. That's why I'm going to leave it for a future video.
Utilities are adding more and more sophisticated sensors to the grid. And this means one thing: more information.
If you have fairly frequent critical tasks, then it will happen sooner or later that every few days your car or your smart grid will take the wrong decision because the computer did not react fast enough, for example.